In this last section of Chapter 11, and in fact the last section of the entire course, we will cover one last theorem called the binomial theorem, which involves a couple of different elements out of sequences and series. We did introduce in this chapter the mathematical operation called the factorial. You will see that in this section. And we will look at a specific sequence of numbers formed by those factorials, something called the binomial coefficients. And with that, let's get started. Let's talk about what does the binomial theorem allow us to do. The main thrust of the binomial theorem is to provide an efficient formula for expanding a binomial raised to a power. Now, the first few of these are pretty obvious, but let me point out the fact that we are looking for some sort of pattern that will allow us to do this quickly without having to manually actually distribute all of the terms. Look at this. Of course, a plus b raised to the 0 is 1, because anything raised to the 0 is 1. And of course, a plus b to the first power is itself. Now, a plus b squared is what you get if you take a plus b times a plus b and FOIL. First, outside, inside, last, gives me a squared plus 2ab plus b squared. Now, if I wanted to do a plus b cubed, that would be a plus b times a plus b times a plus b, all three of those. Now, because I know the first two are already a squared plus 2ab plus b, plus b squared, I would then take that times a plus b again, distribute all the terms, collect like terms, simplify, and I'd get this. Now, I want you to think in your head how much work that would be. Okay, to multiply a squared times a squared times b, 2ab times a, 2ab times b squared times a, b squared times b, and collect like terms and simplify. If you did all of that, you would get this. A cubed plus 3a squared b plus 3ab squared plus b cubed. Now, keep going. A plus b to the fourth. Okay, this is what you get. A to the fourth, 4a cubed b, 6a squared b squared plus 4ab cubed plus b to the fourth. If you do a plus b to the fifth and multiply it out, here's what you get. A to the fifth plus 5a to the fourth b plus 10a cubed b squared plus 10a squared b cubed plus 5ab to the fourth plus b to the fifth. Now, can you guess what this expansion would look like? Okay, well, in every case, look how the first term grows. Right, it looks like a to whatever the power is, and the last term is also b to whatever that power is. Okay, and here's what you get. The next one is 6 a to the fifth, and then b. Okay, the next one after that is 15 a to the fourth b squared. Now, I don't want you to feel bad if you don't see where all of this came from. I want to identify some important properties or patterns that I recognize that allow me to get this far. Plus 20 a cubed b cubed plus 15 a squared b to the third. Right, let me scoot my little b to the sixth over. Boom, right there. Make sure I got this right. 6a to the fifth b, 15a to the fourth b squared. That's 20a cubed b cubed plus 15a to the second b to the fourth plus 6ab to the fifth plus b to the sixth. Okay, so what did I notice that let me write that down without having to actually multiply it out? Let me point some things out to you. The first thing to note is that there are n plus 1 terms in the sequence, where n is the power. Okay, how many terms did I have? 1, 2, 3, 4, 5, 6, 7. Right? In the previous one I had 6. Previous one before that 5, 4, and so on. It's n plus 1. The first term is a to the n. The last term is b to the n. Now, as you read from left to right, the exponents of a do what? In every case, they start at n and they go down, right? N and go down until they get to 0, right? The last term doesn't have an a in it, so that's the same thing as a to the 0. So the exponents of a decrease by 1 from term to term, and the exponents of b, they start with no b, so b to the 0, and they count up, b to the first, b to the second, b to the third. So they increase by 1 from term to term. Okay? Now the sum of the exponents in each term is what? Here there's only a 6, so it's 6. This is 5 plus 1, you get 6. 4 plus 2 is 6. 3 plus 3 is 6. 2 plus 4 is 6. Wow, it's always 6, right? So it's always n. 6 happened to be the power I was raising it to. The other thing I want you to see, and you may not be able to see where they come from, but at the very least the coefficients are symmetric. 1, 3, 3, 1. 1, 4, 6, 4, 1. I'm just listing the coefficients of each term. 1, 5, 10, 10, 5, 1. And then 1, 6, 15, 20, 15, 6, and 1. Notice how they're symmetric right down the middle, right? You draw a line down the middle, and it's the same on either side. Okay? Now, how do I determine the coefficients? I can already determine what the variables are going to look like, okay? Because I know the powers for the a decrease by 1, but they start at n, and the powers for b increase by 1, but they start at 0. But the coefficients, how do I figure them out? One way to determine them is something called Pascal's triangle. What in the world is Pascal's triangle? Let's take a look. Alright, here's Pascal's triangle, and here's how I would write it out. Start with just a 1 at the top, and then put a 1 and a 1. I'm going to have a row that's increasing in size each time down. Now what I'm going to do is I'm always going to start and end with a 1. What I'm going to do is between the two numbers above, I'm going to add those two numbers. What's 1 and 1 added together? It's 2, and then stick a 1 at the end. Okay? Now 1, and if I'm between two numbers, I'm going to add them up. So 1 plus 2 is 3, 3, 1. Okay, start with a 1, and then between the 1 and 3, add that up and get 4, 6, 4, 1. I have a 1 and a 5, 10, 10, 5, 1. And a 1 and a 6, because 1 plus 5 is 6. 5 plus 10 is 15, 20, 15, 6, and 1. Now what do you notice about these? These are familiar because I just wrote them above whenever I was looking at the coefficients of that expansion. In fact, look right here. Those are the coefficients for the b to the 6th, or the a plus b to the 6th. 1, 6, 15, 20, 15, 6, 1. So the row of the Pascal's triangle corresponding to that power is always going to be the coefficients for that expansion. So this was n equals 0, n equals 1, n equals 2, 3, 4, 5, and 6. So we were on row 6. So we now have everything we need to expand using this pattern that we've established. Now that pattern is what we're going to call the binomial theorem. Okay, so before we actually state the binomial theorem, let me give you another way of finding those coefficients, because sometimes one method is better than the other. The first technique I gave you was Pascal's triangle, but there's also something called the binomial coefficients. So the binomial coefficients have a particular formula, and they look like this. For an n and an r, where they're both non-negative and r is some number between or from 0 up to n, we would write in parentheses an n and an r, but no bar. It's not a fraction, it's just the notation for binomial coefficients. is given by this formula. You take n factorial. Remember, n factorial is n times n minus 1 times n minus 2 all the way down to 1. You just keep multiplying, starting at a number going down to 1. And then take n and subtract it by r. Take r away from it. And then that number, take the factorial, and also divide by r factorial. That is what's called the binomial coefficient. So, for example, if I wanted to find the binomial coefficient of 5, 2, which is sometimes read as n choose r, for reasons that would make sense after you have a little bit of statistics and probability, this also turns out to mean the number of ways that you can choose a subset of size r out of a group of n objects, where order doesn't matter. But n choose r, in this case 5 choose 2 would be 5 factorial over 5 minus 2 factorial 2 factorial. Now what I prefer to do is write out the product and then cross out common factors in the numerator and the denominator. So 5 times 4 times 3 times 2 times 1. So I could leave off the 1 because it doesn't matter. 5 minus 2 is going to be 3 factorial, so that's 3 times 2 times 1. 2 factorial is 2 times 1. Now let's divide out common factors here. So the 3's divide out. I can take this 2 and this 2. This 2 goes into the 4 twice, so I have 5 times 2, which is 10, right? 5 times 2 times 1 over 1 times 1 is 10 over 1. So 5 choose 2 is 10. 6 choose 4 would be 6 factorial over 6 minus 4 factorial, 4 factorial, which I would write out 6 times 5 times 4 times 3 times 2 times 1 divided by 6 minus 4 is 2, so 2 factorial is 2 times 1, and 4 factorial is 4 times 3 times 2 times 1. Notice how those cancel out right here. 2 goes into 6 3 times, so I have 3 times 5, which is 15. In other words, based on what I said before, there would be 15 different ways you could take 4 objects out of 6 objects, a subset of 4. If you had 6 paintings, for example, but you only had 4 spots on the wall, and you wanted to hang those 4 up, it didn't care what order they were in, so different order you wouldn't count twice. How many ways could you choose 4 out of those 6? And the answer is 15. Now this one, if I ask that same question, I can answer it without working the formula, but let's answer it both ways so that we can see that the formula makes sense. If I said I had 9 places on the wall and there were 9 paintings, how many ways could I hang those up? Order doesn't matter, right? So there's only one way to choose 9 out of 9, right? So I should get 1 as my answer. So 9 factorial over 9 minus 9 factorial, 9 factorial. So that gives me 9 factorial over 0 factorial, 9 factorial. The 9 factorials cancel. Remember that by definition 0 factorial is 1, so I have 1 over 1, which is 1. That's my final way, the only way I can choose 9 objects out of 9. Now, again, the point here is that the binomial coefficients are this choosing operation, so they're going to show up in the binomial theorem as a way to calculate this. But we have 2 ways of getting those numbers, and these numbers are either going to be things we can calculate with the formula or using Pascal's triangle. Now let me recommend that in most cases we're going to use Pascal's triangle for our problems. So here's the binomial theorem stated. The binomial theorem says, if I can spell, sorry, that a plus b to the nth is the following. You take the binomial coefficients with n all the way across in the top, so the coefficients are where the bottom number marches from 0 up to n. Okay, a to the nth power a to the n minus 1 power, a to the n minus 2, all the way down to a to the 0, and b goes from b to the 0, b to the first, b to the second, all the way up to b to the n. Exactly what we saw in our pattern above. And I can write this in the condensed form using summation notation. I don't care which formula you use to remember this, but the point here is that we have a way of writing down the binomial expansion when we take a binomial raised to the nth power. Now let me note again for you here that n0, n1, all the way up to nn is the nth row of Pascal's triangle. So we can actually come up with those coefficients by finding Pascal's triangle, go down to that row, and then we wouldn't have to actually use the factorial formulas to calculate those, which saves us a little bit of work. Now we will do a couple of examples of using the binomial theorem to expand. So here's what I suggest that you do. When you see something like this, you're going to recognize, first of all, that the first term in the binomial is what I'm going to refer to as A. The second term is what I'm going to refer to as B. And the power is N. Okay, so here's what you'll have. You're going to have three things in each term. And how many terms are you going to have? You're always going to have N plus 1 terms. So in this case, I have 5 terms. Okay, the first thing are the coefficients. Now, how do I find the coefficients? Well, I go to Pascal's triangle. I go to the fourth row. 1, 1, 1, 1, 2, 1. That's the third. So this is 0, first, second. 3, 3. That's the third row. 1, 4, 6, 4, 1. There's my fourth row. So 1, 4, 6, 4, 1 of the coefficients. Now take the a's. I'm going to start with a and raise it to the highest power, that is the fourth. So I'm going to have x to the fourth, x to the third, x to the second, x to the first, and x to the 0. Then I'm going to take the 2, which is b, and raise it to increasing power. So 2 to the 0, 2 to the first, 2 to the second, 2 to the third, and 2 to the fourth. Now I've got to simplify each term. Now 2 to the 0 is just 1. So I have 1x to the fourth, so that's x to the fourth for my first term. Alright, I'm going to have a 4, and 2 to the first is 2. So 4 times 2 is 8. And I have an x cubed plus. Now 2 squared is 4. 6 times 4 is 24 x squared. 2 cubed is 8. 4 times 8 is 32. 32x to the first. Now x to the 0 is 1. 2 to the fourth is 16. 1 times 16 is 16. This is the polynomial that you get when you expand x plus 2 raised to the fourth power. Now don't get too excited, but this is the last example of the entire semester. So let's do the exact same thing again. Let's walk through what we get whenever we do our binomial expansion. Now we're going to have 6 terms here, right? So 1, 2, 3, 4, 5. Let's go ahead and put one right there for good measure. Now what does the fifth row of Pascal's triangle look like? Now I'm going to borrow this and just keep going. That was the fourth row. So 1, 5, 10, 10, 5, 1 is the next row. So 1, 5, 10, 10, 5, 1 are those terms. Now I'll take 2x. Now I'm going to put it in parentheses because I've got to raise the whole thing to this power. 2x to the fifth, 2x to the fourth, 2x, 2x to the third, 2x to the second, 2x to the first, and 2x to the 0. Now look at this right here. The minus sign means that whole thing is b. So I'm going to have a negative y to the 0, a negative y. You got to include that minus sign because your original formula had a plus in there. If there's a minus sign, you've got to stick it in somewhere. That means you're going to include it as part of b. Negative y to the first, negative y to the second, negative y to the third, negative y to the fourth, and negative y to the fifth. Again, all you're doing is taking the a and starting at the fifth power and marching down. You're taking the b at the 0 power and marching up. Now I need to simplify each of these terms. Now 2 to the fifth is going to give me 32. I've got an x here, and anything to the 0 is 1, so I have 32 x to the fifth power, x to the fifth. Okay, next I have 5. 2 to the fourth is 16. 5 times 16 gives me 80. But I've got a minus y here, so that means that this is going to be a negative. All I'm doing is taking 5 times 2 to the fourth times negative 1 gives me a minus 80. I have an x to the fourth and a y to the first. Next, here I have a 10, 2 to the third is 80, and a negative squared is positive, so I have plus 80. I have the x cubed and a y squared. Okay, the next one I'm going to have a 10, and I'm going to have 2 squared, which is 4. I'm going to have a negative 1, so that gives me a minus 40. I got the x squared and the y cubed. Squared y cubed. Okay, that's going to be 5 times 2, and then I've got a positive 1 because negative raised to the fourth is positive, so plus 10 x to the first, y to the fourth. And then the last one I've got, that's all raised to the 0 power, so it's all 1. I'm just going to have a minus y to the fifth. And there is your binomial expansion of 2x minus y all raised to the fifth power, an application of Pascal's triangle. And that is the end of section 11.4 and all we're going to cover about sequences and series in college algebra. Thank you for making it this far in the online course of college algebra at Wayland Baptist University. The end.